Hello everyone. This is the first part of the states of matter video. In this video, the subtopics that you will be learning are binding forces of molecules, inter and intramolecular forces, attraction and repulsive forces, van der Waals force, hydrogen bonding, ion dipole bonding, and vapor pressure. Hopefully this video will be beneficial for you. Thank you.
Binding forces in molecules. There are two types of forces that we consider when we study molecules. One of it is intramolecular force. It is the forces between particles within a molecule which holds the molecule itself together. Another one is intermolecular force, which are the forces that exist between different molecules. It is actually a weaker force than intramolecular force. What happens when the molecules interact? Of course, they may react, the bonding patterns rearrange, atoms find new partners, and new molecules are formed. But molecules will interact even when they are not forming chemical bonds. They are known as the non-bonding interactions, which produces the repulsive and attractive force. As the energy increases at first, the repulsion is more than offset by the attraction between nuclei and electrons, but at a certain point, as the nuclei get even closer, the repulsive force begins to overcome the attractive forces.
Van der Waals forces. They include attractions and repulsions between atoms, molecules, and surfaces as well as other intermolecular forces. They differ from covalent and ionic bonding and are caused by correlations in the fluctuating polarizations of nearby particles. The picture below shows attractive interactions resulting from dipole-dipole interaction of two hydrogen chloride molecules. Van der Waals forces can be divided into a few major contributions, that is, forces between two permanent dipoles, which is also sometimes known as Keesom force, force between a permanent dipole and a corresponding induced dipole, which is also sometimes called Debye force, and also force between two instantaneously induced dipoles, which is also known as London dispersion force.
Ion dipole and ion-induced dipole forces operate more like dipole-dipole and induced dipole interactions, but involve ion instead of any polar and non-polar molecules. These ion-induced dipole forces are stronger than dipole interactions because the charge of any ion is much greater than the charge of a dipole moment. Ion dipole force consists of an ion and a polar molecule interacting. They come in a line so that the positive and negative force are next to each other, allowing for maximum attraction. Now imagine two water molecules. The positive charge of one molecule, hydrogen, will be attracted to the negative charge of the other water molecule on the oxygen. So, as intermolecular force which holds the two together. Ion-induced dipole force consists of an ion and a non-polar molecule interacting. Like a dipole-induced dipole force, the charge of the ion causes a distortion of the electron cloud on the non-polar molecule. For example, oxygen molecule. There is no clustering of electrons in any region of the molecule. What is important to remember though is that electrons are constantly flowing around the electron cloud of the oxygen molecule. So at random times, there will be more electrons in one area around the oxygen molecule than other areas. As a result, a temporarily negative area of one oxygen molecule can interact with a temporarily positive area of another oxygen molecule and bring about a small interaction. A hydrogen bond is the electromagnetic attractive interaction between polar molecules in which hydrogen is bound to highly electronegative atoms such as nitrogen, oxygen, or fluorine. The name hydrogen bond is something of a misnomer as it is not a true bond but particularly strong dipole-dipole attraction and should not be confused with a covalent bond. This hydrogen bond attraction can occur between molecules intermolecular or within different parts of a single molecule intramolecular. The hydrogen bond 5 to 30 kilojoules per mole is stronger than a van der Waals interaction but weaker than a covalent or ionic bond. This type of bond can occur in inorganic molecules such as water and in organic molecules like DNA and protein. The bond energy is the measure of the amount of energy needed to break apart one molecule of covalently bound gases. The SI unit used to describe an energy is kilojoules per mole of bond. The difference between bond energy and lattice energy. Lattice energy is the amount of energy required to break up an ionic compound. Bond energy is the amount of energy required to break up a covalent compound. The trend for both is the same though. Ionic example: sodium chloride versus potassium bromide, which has the highest lattice energy and which is harder to break up. Since the charges on all four ions are either positive 1 or negative 1, you just look at the size of each. Since sodium chloride is smaller than potassium bromide, it holds together tighter and has the highest lattice energy. Covalent example: aluminium fluoride versus fluorine gas, which has the highest bond energy and which is hardest to break up. Since both have one fluorine in common, you look at the other atom and decide which is bigger. Fluorine gas has the highest bond energy, since fluorine is smaller than aluminium and is harder to break up.
States of matter. The primary states of matter or phase are gases, liquids, crystalline solids. A phase describes a physical state of matter. The key word to notice is physical. Things only move from one phase to another by physical means. If energy is added or if energy is taken away, physical change happens. The characteristic of solids: they hold their shape, they don't flow, they are not allowed to move around, molecules are stuck in a special arrangement of atoms, atoms still spin and electrons fly around but the entire atom will not change position. Solids with high vapor pressure can pass directly from the solid to gaseous state without melting at room temperature. This process is known as the sublimation, and the reverse process is known as the deposition. If a solid material is heated enough, it will reach a point at which it melts. The energy needed to turn a solid into a liquid is called the enthalpy change of fusion. If a liquid is heated enough, it will reach a boiling point. The energy required to turn a liquid into a gas is called the enthalpy change of vaporization or heat of vaporization.
Gas. You can feel gas when the wind blows. Is made of many gases and is all around you. A gas is matter that has no shape, size, or color of its own. As the temperature of a gas increases, when energy is added, the atoms move quickly, become widely separated, and spread out in all directions. The atoms spread out equally in any container it is in. Think of a balloon. The atoms are spread equally throughout the entire balloon. The forces of attraction between the constituent particles are being ignored due very high kinetic energies, which are more than sufficient to escape from the attraction of other particles and tend to maintain very long distance from each other. The particles in the gas move randomly in all directions with very high velocities and tend to deny the gravitation force of attraction. The actual volume of the constituent particle is big enough when compared to the volume of the container.
Liquid states of matter. What is liquid state of matter? A liquid that has a fixed volume at given temperature. Properties of liquid. Assume that the shape or part of the container which it occupies cause particles can move or slide past one another. Not easily compressible cause there are little free spaces between particles. Lastly, it flows easily cause particles can move or slide past one another. Diffusion in liquid. For example, colored crystals. Highly colored salt crystals, potassium manganate, are dropped into a beaker of water. Bright purple color of dissolving salt slowly spreads throughout all of liquid, but it's much slower than gas because of the greater density of particles.
Vapor pressure of liquids. What is definition of vapor pressure? It is defined as the constant pressure exerted by the vapor, gases or liquid substance in equilibrium with its solid or liquid phase. What is dynamic equilibrium? Dynamic equilibrium is when two opposing processes occur at the same rate, for example condensation or evaporation process. When this occurs, the vapor is said to be saturated. Dynamic equilibrium does not occur in open container. Therefore, open containers do not have vapor pressure. Diagram on the left shows the high vapor pressure evaporates more quickly and is volatile. For example, gasoline. If low vapor pressure evaporates more slowly and is not volatile. For example, motor oil. The line graph shows that the increase in temperature also increases in the vapor pressure. This proves that dynamic equilibrium does depend on temperature. Vapor pressure can be calculated through the Clapeyron equation that's stated on the slide, where P1 and P2 is the vapor pressure at absolute temperature, which is the T1 and T2, while the delta HV is molar heat of evaporation, that is the heat absorbed by 1 mole of liquid where it passes into the vapor state.